Well, great. Good morning. We are we're having to go live this morning, so I think this is the recording that I will post for the rest of the afternoon. So don't just look forward, and they won't see you. They won't know who you are, and I'm gonna be careful not to use names. Dude, are you? Oh, I think you're okay anyway. Yeah, don't look. Can you hear me over there? Hello. Like a faint echo. Oh, and can you? So what do you guys see? Do you see this room and you see that screen? Yeah. It sounded like one of you had. You just do? Okay. Because you're probably using your non-school account, right? Okay, so let's start. Let's start the fun. Maybe that's an exaggeration. Maybe it's not. You're going to have to sit through class and decide on your own. I'm not going to tell you what to think. I'm not going to even pretend. I'm not going to even pretend I know what to think, because honestly, I've thought about it and I don't. Do you know how confusing that is if you don't know what to think? Yes, sir.
My test. Remember, we talked about it on Monday.
Yeah. You're going to do it right now?
I thought that's what we talked about.
Okay. You need a desk. Are you doing the point recovery quiz? No. You need a, yeah, you need a desk in the hallway. So can you just grab this one and go out there? Grab a calculator. You're right. I forgot. And it looks like Haley is here. And, well, Troy, you don't count because you're here twice. I mean, you count, Troy. Yeah. You count, Troy, but you're actually here and you're there. So, you know, you're in the chat. If there's someone who's got a question, can you raise your hand and tell me what's being said? All right, excellent. Let's start. So we are going to look at today, we're going to start looking at fairly robust equations. In fact, if you were to just see 10 of these equations right now and I ask you to solve them, you just think your head like, this is not possible, right? But we've done a lot of laying of the groundwork, and we've gotten to a point where we have a lot of tools to make equations that look very, very unpleasant simple, right? And you're going to see that today. I would like for us to start with a little review of what we did yesterday. So this is where you guys are going to pick up in your notes. Remember, I'm being much less labor intensive in terms of, oh my gosh, you guys have to do this, this, and this for the class assignment and then the homework. All I want right now is the upload of the notes. So if you could just label the top of this 3.3.1 lesson notes, and it should be about a page and a half, not more than 2 pages. And you'll just upload those to our friends in the cloud, and we'll be able to look at those up there sometime soon. I'm gonna make this screen. I'm gonna make this screen go away for just a minute, and then I'm gonna make this screen come back. There we go. Oh, we apparently see everything, huh? We see it now. Good. Wait, can I go back? Oh, I hid that one. Okay. So let's start. So yesterday we talked about the fact that sometimes when we want to multiply things, like we might have to use an area model. So just by way of vocabulary review, what I'm looking at here is a binomial times multiplied by another binomial. And that word binomial just means that each one of those has 2 terms, and those 2 terms are things that are separated by the plus and the minus symbol. So in that first binomial, my terms are 6x and negative 11. And in the second binomial, my terms are 2x and 5. So if I wanted to show how to multiply that and get all of the parts of the answer, right? Go back. An area model would really help me organize my work. So I'm going to come in here and I'm going to draw a generic area model. I'd like for you to sketch one as well. Don't make it super big. This is your notes. It's not like you're trying to get it on a screen. Across the top, I'm going to go ahead and write the 6x, and I'll also write the negative 11. And then down on my left-hand side, we're going to write a 2x, and we're also going to write a positive 5. So what we're looking at here is what's the product, right? So if I was to think about this product, in the upper left-hand corner, yeah, they're yours to use. Yeah, just make sure you leave it out there so I can spray it down with alcohol when you're done. So this upper left-hand box, right? What is the value that I put in the upper left-hand box? Can you tell me, Dave? It's exactly 12x squared, right? It's 2 times 6 is 12, x times x is x squared, right? To the left of that, what do we have, Gibson?
To the left of that?
Yeah.
We have negative 22x.
We do, negative 22x. Right below that, we have negative 55. If you look, what I'm doing is I'm multiplying the negative 11 times the 5 and getting a negative 55. And then to the left of that, I have 30x. So I've written this area up here as a product of two binomials, but I can also write that it equals the sum of the parts. So I can transform that into 12x squared plus 8x minus 55, okay? Now, we can do this if we've got a binomial times a trinomial or polynomial with 4 terms times 3 terms. It's just that the size and dimensions of our generic area model get larger, and there's a lot of little pieces we have to look at. But when you're multiplying something that's got like 4 terms by 4 terms, there are literally 16 different things there. And you do not want to have to keep track of those 16 different things. What you want to do instead is say, I'm just going to make a generic area model and see what's in each of those pieces. And like here, right, what happens is sometimes those pieces can be combined. So the negative 22x and the 30x do combine to form a simpler version of that, just 8x. All right, the next one over is what our textbook yesterday called the simplest form of the distributive property. It's by far the easiest form of the distributive property. And if I was to rewrite this using the distributive property, I could choose to use an area model, but I don't need to. But if I was going to use an area model, on one of my dimensions, I would just have the negative 2x squared. On the other dimension, I would have 15x to the second power, and I would have a negative 3y. Oh my, right? Negative 3y. Those are some powerful powers of x. And let's not forget, we've got the y in there, right? So for this first box, right, the one to the left, I'm multiplying negative 2x squared times 15x squared. I can handle the negative 2 times 15. That's going to be negative 30. But when I multiply x squared times x squared, that's 4 factors of x, right? Well, I show 4 factors of x by writing x to the 4th power. So what I've got there is negative 30x to the 4th. And then for the other part, I'm going to have a positive, because I've got negative 2 times negative 3 is positive 6. There's an x squared, and then I'm multiplying by a y. So 6x squared y. Wonderful. Wonderful. I would probably almost never use an area model in this case, right? Because when I'm looking at it, I can just say, look, I'm just going to be multiplying this negative 2x by both the 15x squared and by, don't forget its sign, because the sign sometimes gets missed, and this negative 3y. So I'm just going to do those multiplication problems. All right, let's move forward. You guys ready to move forward? Now, this next equation you're going to see it, and within seconds, you'll know the answer. Right? In fact, you probably know the answer right now if you were to guess, because it's going to be an easy answer, and you'll know it immediately, okay? My point is not for you to think that this is a difficult equation. My point is I want to give us something that can illustrate different techniques that we want to give names to. Because listen, if you give something a name, then you can talk about it. right? So what we want to give these things their names is so I could say, well, maybe we should try this technique or this technique, right? And if they don't have names, it's harder to communicate that. So we're going to look at a very simple problem. And we're going to come up with some names for it. So here it is. Oh my gosh, please do that. Write it down at the very top and then give it 3 little columns. They don't have to be very big. They can be pretty short. They can be half that size, right? At the very top, we're going to write 4 times the quantity of x plus 3. And then we're going to write that equals the number 20. Now, I know you're like, oh, it's 2. It is 2, right? Right? It's 2. It's 2. We're done. We're algebra geniuses. We never have to worry about it again. It's 2. Right? Well, unfortunately, if the world had just that as its problems, right, we wouldn't need any problem solvers because we'd have everything squared away. There's more complexity that we'll have to deal with. So this is just for us to illustrate some techniques. The first technique I want to illustrate is kind of based on what we just did, right? What we just did on the previous couple problems, those two, was we rewrote an expression. We had an expression that was expressed as a product, and we wrote it as a sum of parts. So one of the things I can do is I can rewrite the left-hand side of this using this distributive property. In fact, right below here, I'm going to write that, oh, that's the same as 4x plus 12 equals 20. Now notice I didn't do anything to the right-hand side. I only modified the left-hand side. And that's totally okay because what I wrote down on the left-hand side is exactly equivalent to, right? It's equivalent to what I had before. So as long as what I'm writing down is equivalent to what I had, I can totally rewrite chunks of my equation like this. Now, the next thing, of course, is I have to take away 12 from both sides. I get 4x is 8, divide both sides by 4, x is 2. So that's one way to think of this equation. And I'm going to give this a name. I'm going to call this rewriting. Now, what's interesting is not only did I engage in rewriting for the first step, but my second step used some of the other techniques that you already know, right? We'll give them names too. But I rewrote part of that, and then I used some other techniques. The next thing I'd like to think about is, let's see, where do we want to go with this? I know what we'll do. We're going to talk about this idea of reversing what has been happening, right? So if you look at this thing that I'm underlining in red, right, something is happening to that chunk of parentheses, right? In fact, we are multiplying it by what? Yeah, I can, because every operation, almost every operation in mathematics has what we call an inverse, a way to undo it. So I can undo multiplying by 4 by using which operation? Yes, absolutely, right? I can divide that by 4. And in fact, to be precise, if I divided both sides of this equation by 4, right, this would become x plus 3 on the left-hand side. And on the right-hand side, it's just going to become the number 5, right? So I'm undoing an operation. I'm undoing something that was done. Turns out these parentheses aren't holding any information for me because there's nothing, not a positive sign, not a negative sign, not a value that I need to distribute. So I can rewrite it by just eliminating the parentheses. But I just undid division by, I undid multiplication by using division. In fact, I can do that again, right? I can undo addition of 3 by engaging in this subtraction of 3. So there it is. Undid things twice. I was adding 3. I undid that. Right here, I undid adding 12. I undid multiplying by 4. First, I rewrote it, right? First, I rewrote not the whole thing, but I just rewrote the left-hand side. But then you can see I did undo, undo. Okay, that's nice. That's nice. Let's move along. One more way that I want to be able to talk about. Oh, I didn't call this undo. Undo. Let's put it in ing. Undoing, right? That sounds like I'm doing something, but I'm undoing it. Rewriting, undoing. The last thing is very mysterious, right? It's like, really? That's what we're going to call that? It seems a little interesting, but if I look inside of those set of parentheses, do you guys know what x plus 3 has to be? It has to be 5, right? I can look at it and say, well, I know this. That got to be 5. Why? Well, because 4 times 5 is going to give me the 20, right? So this is not the best example of this. We'll see more examples of it. But sometimes it's nice to look inside and say, hey, what's this thing have to be? What does this have to be in order for this to work? And it turns out that thing has to be 5. And I just wrote it down. And you're like, what did you do? I looked inside and I said that x plus 3 has to be 5, right? So, and then of course I'll undo the adding 3. I'll just write x's too. But what I do here, I was looking inside. And we'll see a couple examples of that today too. Looking inside. So we're going to call these 3 techniques this. And we're going to get to where, and not next, but right after that, we're going to get to where we're going to start seeing kind of robust examples. And it'll be like, wow, the training wheels are off, or at least one side of the training wheel's off. We have to this way or else we'll fall over. By the way, I really like how now kids have bicycles with, they don't have the training wheels. What they have is no pedals. Have you seen that? Did you have one of those? You just scoot around. Only 2 wheels with just no pedals, but you learn balance, right? You learn balance. And then as you learn balance, then you can throw the pedals in later, right? But at first you learn balance and you got your 2 feet there. Because man, when they take the training wheels off, you don't know balance. That's scary. Like that's now you're running 2 things at once, right? Did you experience the training wheels or did you go to the balance method? You rode a bike, it's very good. You just went right to it. Huh? You were like, hey, I'm 2.5, give me my bike, right? Yeah, that's nice. When did you start riding a bike? Do you know?
I don't know. I was kind of older, and I got really scared.
Another bicyclist?
No, person in a car.
Okay. Yeah. Troy, how about you? When did you start riding the bike?
Like 5.
Yeah. Amira? That around there. Yeah. Me too. Okay. So we're going to move forward now. And what's going to happen next is I'm going to give us 3 different scenarios. Scenario A, B, C. And we're just going to identify based on what they said, is this an example of looking inside? Is it an example of undoing? Is this an example of don't say it, rewriting a chunk of the equation, right? Rewriting a chunk of it. So to be honest, if they gave us just a problem, you could mix these up, right? But they're going to give us a bigger scenario. So let's look at C first here. It says, we're going to look at the bottom one. So in C, it says, hey, this problem might be easier if I turn the 4 times the quantity of 2x minus 3 equals 31 into 8x minus 12 is 31. So what will we call this? Yes. Yeah, we totally replaced this expression with something that's exactly the same as it. So this is a perfect example of what we're going to call rewriting. So up here, I'm just going to put C. Now, there's a lot of writing for you to capture all of these steps. So don't do that. We don't need to get that into our notes. But you can see, right, what's happening here is like this thing, if I look at it differently, it might be easier. We'll call that rewriting. Now let's back up and go to B. B says, quote, subtraction is the opposite of adding. So for the equation 3 times the quantity x minus 7 plus 4 equals 23, I can start by subtracting 4 from both sides. So what would we call what's here listed as B? What do we think this is? Say it, somebody. Oh, you know. Say it. Yeah, thank you. Somebody said it, thank you. This is an example of undoing, so I'm going to put the letter B here. Again, you don't need to write these down. This is actually in your book, this part, so if you want to refer to it, okay. So we undid adding 4 by subtracting 4. Then this last one, And I don't know why they put this first. It seems kind of confusing. I don't know if you've noticed this or not, but if I have 5 that's raised to a power like this, the only way that these are actually equal to each other is if the exponents are the same. Oh, 5 is 5, right? Oh, 25 is the same as 25. Oh, if I put a 3 there, 125 is the same as 125. In order for these to truly be the same, right, to be equal to each other, those exponents have to be the same. So because our bases are like this, our bases are both 5, I can engage in this thing where I'm saying, oh, this 8x must be 24. Do you know what I'm doing? And I'm saying, hey, if these are going to be the same, that exponent, what's inside that exponent has to be the same as what's inside that exponent. So we will call A an example of looking inside, okay? Looking inside. Okay. Now it's time for, I think it's almost our time for our finale, which is amazing because we're going to have some time. It's time for our finale. And the reason why I say that is I'm now going to give us 3 robust examples. And I want you guys to make sure you get these examples in there. For all 3 of them right now, we're just going to talk about the technique of rewriting. So our friend, our ally is rewriting right now. Are you ready to do some rewriting? Yeah. You know, yesterday, like some people came in to retake tests, and it was the weirdest thing because there were very few people in here, and I had all the windows open. I said, if you sit way back in the corner, you can take your mask off. I didn't recognize these people. I don't know, really, I don't know what you guys look like with your mask. Well, I've seen pictures now. They've showed up in Aries. But I was just like, I was looking at this one kid. I'm like, who are you? Right? Who are you? Kingston. Do you know Kingston? No, you don't know that guy. Who do you know him?
Trent.
Yeah, Trent. I'm looking like the whole time, like from here up, he reminded me of the student I had in class like a few years ago. And I looked at from here up and I put in the rest of his face from that guy. He took his mask off, like, who are you? Right? It's just weird. Just weird. Okay. We're ready. First example, rewriting the express 3. The first one. Okay. Well, I'm not a fan of the right-hand side. The right-hand side, it's difficult for me to deal with this binomial times a binomial. But fortunately, we've done a little bit of work, and I think that I can rewrite that left-hand side, turning that product into a collection of sums. I can turn this multiplication problem into some terms. And across the top, I might write an x and a -1. And I could put a 5x and a 6 here. One of the things you noticed yesterday, I hope you noticed this when you looked at the answers, is that it doesn't matter if I switch them. I put the x minus 1 on the left-hand side and the 5x plus 6 at the top. I'm still going to get the same product. And even if I was to switch the 5x and the 6, if I move those over, I would still get the same product, right? It would switch these 2, but it would still be the same product. The one thing that I couldn't switch is I couldn't make this 1 minus x, right? 1 minus x would be a that thing, right? Some of you have a teacher that told you whenever you see a subtraction problem, don't leave it like that. Just make it like this. Because if you do that, now you could switch them, right? You could write that as -1 plus x. And if you went that route, it would be the same. So I want you to understand that sometimes when we multiply these things, there's only one product, right? There's only one product. But the order that they populate the boxes could be different, but it's going to be equivalent to it. So in my upper left-hand corner, when I look at the fact that I am multiplying, I'm multiplying 5x times an x, I will get 5x squared, right? 5x times x is going to give me 5x squared in that corner. In the other corner, when I'm multiplying a 6 times an x, this is going to give me 6x. To the left of that, I'm still multiplying by 6, but this time by a -1. And 6 times -1 is -6. And then I'll use a beautiful purple for this other corner. I'm multiplying here 5x times a -1. And when I multiply 5x times -1, I get -5 and x. So you can see the parts that we get, and it turns out that two of the parts, right, the 5x, -5x, and the 6 times x are the same terms. They're like terms, so I can combine them. So I can rewrite the left-hand side as 5x squared plus a single x minus the number 6. Okay. I'm just going to copy down this left-hand side, 5x squared plus 43. Now, happy day, oh happy day, the fact that there's a 5x squared on both sides makes this very, very, very wonderful, because if you have equal things and you take away equal things, you get equal things. So right now what I have, it says they're equal, right? And the equality that I have right here, right, is contingent upon this initial statement being true. If that initial statement's true and this is a valid substitution for what was above, right, then these things are still equal. Well, I can go another step. If things are equal and you take away the same thing from both sides, you get equal things. That's why I put that equal there again, because this has to equal this. I had equal things, check. I took away equal things, check, check. I get equal things, check. That's how that works. Let's add 6 to both sides. I get 49 is x. So I would say that x is the number 49. So, it's not like the number 2. If I just looked at this and said, what's the answer? I'm not going to guess that. I'm not going to guess 2. But if I go through this, because 2, 49, but this, I can get that, right? X is 49. By doing what? By rewriting. And then we used properties of equality. I took away the same thing from both sides, and I did some undoing, subtracting 6, etc. Right, so that's example 1. Example number 2. Pachow! There it is. Example number 2. So in example 2, I think we can start by rewriting. I think we can rewrite this, right? We can do this. I've got this -3, and I'm multiplying that by the 1 minus x. Now, I could use an area model, right? But I think I can get this without messing it up. Maybe I can. I think it's going to be x squared minus 3 plus 3x. X squared minus 3 plus 3x. Yeah, I think that's right. Yeah. What do you know? If I wanted to, I could do a quick area model. It would just be a 1 by 2. So I've got the -3 out here and a 1 and -x. This is definitely -3. This is definitely positive 3x. So yeah, that's good. That's good. All right, so what about this other side? That's causing some consternation, right? I got this thing squared. Squared. Could I rewrite that? Could I rewrite it? What do you suppose I get if I rewrite that? Yeah.
Would it be x squared plus 9?
Thank you for saying that. But no, don't write that down. But that's what we would all do, right? I mean, I've been there. I've done that. Exactly that thing, right? And so let's talk about why it's not that. But that is you see it already, huh? That's the best thing you could have said. So thank you. And I didn't, that wasn't a plan. That was just natural. So to square something means to multiply it by itself. So if you look at this, I've got a 2 by 2 that I'm multiplying by itself. So I have in an area model x plus 3, and I'm multiplying that by x plus 3. So clearly, right, we always see that part. you can see we just naturally see the x squared plus 9, right? And the same thing is true if the binomials aren't the same. We always see when I multiply the x's times the x's and the numbers times the numbers. But it turns out there's some pieces there that we missed. So we're going to come in and we're going to grab those missing pieces. And they happen to be, down here we've got 3x, and up here we've got 3x. So they were blind. We were blind to them, but now here they are. We've got x squared plus 6 times x plus 9. Oh, and you can see it, right? The planets have aligned. This is a beautiful moment because both sides have an x squared. So I am going to subtract that from both sides. If I have equal things, I take away equal things, I get equal things. Both sides are losing their x squared, so I've got 6 times x plus 9 is the same as negative 3 plus the 3x. Okay. Let's see. I'm gonna take away 3x from both sides. I'm gonna take away 3x from both sides. That's what I'm gonna do. You could do other things for sure, but if I take away 3x from both sides, this side loses a 3x and it just becomes, instead of 6x, it's now 3x. On the other side, it loses the 3x altogether and it's just negative 3. I can, if I want to, sure, why not? I can subtract 9 from both sides. So I'm going to get that 3x. When I take away the 9 from that side, it's just 3x. And over here, when I take away 9, it's going to be negative 12. That means x is negative 12 thirds, or we would probably just write that as x is the number negative 4. So x being negative 4 is not something I would normally expect. What it is, and we can verify that to a certain extent, right? If I put a negative 4 there, this becomes negative 4 plus 3, which is negative 1. If I square negative 1, this side becomes the number 1. If the other side's the number 1, then I haven't lost it yet. If it isn't number 1, well, I have to start looking at the mistake I made. But it turns out when I square negative 4 times negative 4 is going to be a positive 16. And then over here, I've got a negative 4 and a negative 4 and a minus. No, I've got a 1 minus minus 4. There we go. 1 minus minus 4 is going to be 5. And 5 times negative 3 is negative 15. Oh, you know what that means? Both sides are really 1, right? So I know that that's the value of x that makes this true, because when I plug it in, it made both sides become 1. That's like, yeah, thank you. You know what? I didn't appreciate this until this moment. The head nod means so much in the kind of movie, right? Because sometimes I could see little things in the smile, and even if it's real subtle. Like about 4 of you, I looked around there and you're like, okay, we got it, Rob. Move on. But at least it's just like, oh, you're here. Like, that's nice. I like that. Okay. So last of our 3 examples is coming up. Again, rewriting is what we're all about. Rewriting. Ready? Before we rewrite it, let's write it. Oh my gosh. Let's write that down. Let's write that. That's awful looking. The thing is it will totally cower and run away from us. It will not be a scary thing shortly. We will look at it and say, haha, you thought you were powerful and all wise, but haha, we whittled you down to almost nothing. And we laughed at your insignificance. Getting carried away. Oh, we still have Haley. Troy, you're on twice? Troy's like, I feel sorry. Only 2 people are watching. So Troy's like, I'll watch it twice. No, Troy, I lied. Troy's in there 3 times. Well, how are you doing that? On different tabs? Troy's like, hey, does that mean I don't have to climb the class the next 3 days? Because I'm attending class 3 times right now, right? Okay, Troy. So we've got this written down as is, right? As is, not the best. I think I want to hand this off to someone. Will someone rewrite the left-hand side for me by the way, I don't think there's anything hidden here if you want to do that. No, but you're like, no, Roberts. I didn't mind. Yes, go for it. Thank you.
4x squared minus 2x.
You guys agree with this? So we can see that every single one of those three terms inside was hit with this factor of -2, right? So there were three terms, and they all were multiplied by -2, and that's what we get. So that's our beautiful left-hand side. Before we take much of a look at the right-hand side, I want to point out something, right? There is clearly a giant 1 here, right? That's not a giant 1. Thank you. Can you just set it back on my keyboard there? That's not a giant 1, but when I've got 8/4, right, there is a giant 1 of 4/4. So I want to rewrite that. I'm not going to set it equal to it yet. I want to do some more things with this. I'm going to write this as 2x over y, and I'm going to square that thing. You guys see what I'm saying? So instead of looking at 8x over 4y, that's the same as 2x over y. I just divided the 8/4 and the 4/4. Nice. Now, I'm squaring this, right, which we know means I'm multiplying it by itself. So if I wanted to, I could write it out as 2x on the top, and y on the bottom, right? 2x on the top, y on the bottom. And that's fine in the case of squaring, because it's not a lot of writing. But if that was at the 10th power, I'm not doing it, right? It's too much. So what I notice is because this is only multiplication and division, there's no addition, no subtraction in here, right? In other words, these are all factors or reciprocals of factors. I can rewrite this by bringing things all to the second power. So what I can do is in my numerator, I can say, well, that numerator is going to be 2 to the second power times x to the second power over y to the second power. And this is a great thing, right? If you have a monomial, right? No addition, subtraction. Be careful, right? If you've got a plus or minus some other terms in there, you can't do this. We have to go to an area model. But if it's just one thing and you're raising it to a power, you can raise each one of the individual factors to that power, and you get this instead. So I no longer have, and you know what that just did for us? This is beautiful. Because I was going to bring down this 1 over y to the -2nd, because I was going to say, let's take care of the negative exponent. But what do you just notice happened? Yeah, they took care of themselves, right? It turns out when I multiply y to the second times y to the -2nd, that becomes y to the what power? 0. And what is anything to the 0 power? It's just a 1. So that means this entire thing becomes nothing more than 4x squared. Now, appreciate that. All of this stuff in this green box is nothing more than 4x squared. What? Yeah, why did they write it down like that then? Well, I don't know. It was coming in from whatever they were doing in the field work, and they hadn't done any cleaning up of their expressions yet. But boy, that's a lot easier to work with. Yeah, so here's the thing. I'm so happy you said that, because students do this all the time, and they're like, Mr. Roberts, my equation just died, right? It's like the equal sign's not there anymore. Have you ever done that? It's just like, well, everything went away. What do I do now? No, nothing goes away. Listen to me. If I have 4x squared and I take away 4x squared, what do I get? I get something, right? I don't like it. It's nothing, but it's something. And you're lucky because humanity invented this symbol a long time ago to represent having nothing. Oh, right? Oh, so I took away 4x squared from both sides, and I get, on the other side, -2x plus 10. You have no idea how often it happens that the students will see that they take it away from this side, and then they don't even write the equal, right? It's just, it's gone. It's gone. And I think the reason why we do that is because if there's other things left behind, they're kind of keeping that side alive, right? But if everything else goes away, right, put in this thing to remind yourself there are still two sides of the equation, right? It just becomes this point. To finish this off, I'm gonna undo adding 10, and then I'm gonna undo dividing by -2. And of course, you would more commonly call this just positive 5. There is one other thing I want to point out about this problem, though. You're either Honors 2 or Honors 3 teacher, actually both of them, probably 3 mostly, will appreciate this. There is one little thing that is a restriction, right? Just looking at the original equation, I should point out that this value, y, cannot be 0. And I'm just going to write this there because here's the thing I want you to understand. At our original problem where we began, if y was the number 0, all of a sudden this 8x divided by 0 would become undefined. And if you have something that's undefined and you multiply it by something else, it's still undefined. So all of a sudden, it's like all of that is equal to something that's undefined. So y cannot be 0. If it is, right, if y is 0, we're just like, well, there's no solution, right? You can still do all the work and it'll still give you this 5, but just realize if y is 0, it wasn't there. It was just a mirage. Just a mirage. So anything on your mind? Anything about our homework yesterday or last night? I want to remind you guys today at both lunch, today after school, and today after 7 for ATE. I won't go anywhere. I'll be here. Right? You can do the point recovery quiz. Yes, sir.
Do you still want us to take a picture of this?
Yes. Yeah. So I make sure that when you're in class, that what I do is equivalent to the notes that happen if you're online. So yeah, do submit up an image of the notes daily. Especially when I'm not having you do a bunch of things. We will do some more things, right? But I know last week was crazy. How many of you think last week was crazy in Mr. Roberts' class? Yeah, it was too much work every night. Some people with all those a Google slide thing with like 5 slides is too much. So that's not happening right now. Right, so all of you that are watching online, including all 3 Troys, the Troy triplets, TQ, we'll call him TQ. I'm going to turn you off right now. Stop the recording. So thanks for joining us.